Okay, and I'll try to be concise in view of the time and everyone's empty stomachs and the aroma of pizza wafting into the room. But I do want to begin with a couple of comments about my organizational scheme. First of all, I decided with some thought that the various talks could be divided up into 7 thematic groups. And these I'll present more or less in the order in which they appeared in the meeting, because in fact the meeting was organized more or less in that way. And in fact, I think of this as being organized a little bit like the program for a theater. You have the scenes, and then in each scene, you'll see the list of actors in order of appearance. And so the speakers will be similarly listed in order of appearance, or should I say performers. Now, I do have to apologize, however, to the last 2 speakers. I really didn't have time to assimilate all the interesting things you said and summarize it. And in any case, I hope what you said is fresh in everyone's minds, and whatever I said now would be superfluous anyway. So please accept my apologies for that. And the last comment about organization is that this was an exceptionally interesting meeting, at least in my mind, and I hope in almost everyone's. And a principal reason for that is that everything's so new and it's developing so rapidly that there are hardly any unsettled questions. I'm sorry, hardly any settled questions. Yeah, important correction. And in fact, what I will take away from this meeting is a list of interesting open questions that were raised in our discussions. And what I'm going to do is essentially list a number of those questions for each of those themes. There's only one positive assertion in the entire talk, because I think there's only one interesting new point spoken about at this meeting, which achieved a pretty wide consensus. Everything else, I think, is still excitingly controversial. And of course, the list of just which questions these are and how to pose them is entirely idiosyncratic and subjective. Okay. So, start out with quite a number of talks on actually disrupting the star and the interesting things that can happen. James, for example, began talking about the program of what does happen to the magnetic field of the star. Certainly it gets stretched out into loops by the into the tidal streams, and as those tidal streams loop back out of the orbits, there will be further stretching. At some point, after settling into the accretion flow, it'll be interesting to see what, if anything, the magnetorotational instability does to amplify those fields. There's likely still to be shear, but it does take a number of orbits to saturate to its final amplitude. And this is a transient system, so time is of the essence, and we'll see how the competition eventually works out. Another question that received a good deal of attention was whether small paracenter events, that is measured in gravitational units, are particularly interesting because for them the apsidal precession really is strong enough to lead to fairly rapid circularization. And so might be and so there are various discussions about how common they might be, and also, as we'll talk about later, how observable they might be. A point that actually came up in a private conversation was just about every calculation so far has started out with a polytropic structure for the star because it's easy. Now, polytropes are close to a century old. They're in Eddington's book. We've known a lot about main sequence stellar interior structures for many years now, and I wonder if it mightn't be time to just go to the tables and start out with a realistic structure and see what difference it might make. I mean, surely there must, at the very least, be a quantitative correction in the relation between the radius of the star and the tidal radius. Okay. Then a number of talks raised the question about a variety of sort of interesting special cases with a number of perhaps distinctive properties that we could go look for. Then there was a lot of discussion, and maybe I listed a lot of questions here because I thought about this a lot myself, you can't even see that. There's a light in the way. That is, merge into an evolving accretion flow. I had to push the title way up to the top of the slide to make room for the questions. Okay. And the basic name of the game is that the tidal streams start with very large orbital energies, i.e. very small binding energies, and in particular, quite small binding energies compared to the binding energy corresponding to a circular orbit near the tidal radius, and even smaller compared to the binding energy of stuff that's falling into a black hole, and therefore the potential maximum amount of energy that might be released into heat and thence into radiation. So if we're trying to figure out how to make a bright flare, how does that energy get dissipated from orbital energy into dissipation, into heat, and then into photons, and how many of those photons actually reach observers? So one interesting question is, this is a situation in which, contrary to conventional accretion, angular momentum transport is not necessarily dominated by internal stresses due to correlated MHD turbulence. Instead, shocks can play a significant role. If you have two streams banging into one another, they get deflected. That amounts to an angular momentum transfer. There were comments on that, certainly in James's earlier work, I think back in the early Roswag paper about spreading the angular momentum distribution. There's a figure in Shiokawa et al. It's clearly there, and in this transient situation, an important effect. And in particular, it might be a way to get matter inward relatively quickly. And of course, you could also see it in Olik's simulations. Talk about that more. Now, on the other hand, the corollary of some matter losing its angular momentum by deflection is that the stuff it struck picks up the angular momentum. And it does not then come in easily and gets left behind. And the question is, how does that system then evolve? And I think, for example, in Svi's talk, there were interesting questions raised about how a highly elliptical disk should evolve. And in particular, because in this context, the amount of angular momentum necessary to remove from the streams is not very much bigger than the critical angular momentum for passing through the ISCO. So it might not take very much for those streams just to pass in. And this is also a process that could actually be enhanced by additional deflecting shocks. Okay. Now, I found Olik's simulation of the very close encounter quite interesting, because what the question raised in my mind is, it may be that apsidal precession can create shocks that rapidly circularize when the pericenter is very small, but then you have a lot of material very close in. It has especially high optical depth because it's all crammed in such a small place, and the infall time is also particularly short. And all those put together raise the question of, will we get any light out of it? That'll be interesting to see it actually analyze calculations like that and see how much emerges. We just heard a talk a little while ago about the effects of lens-tearing torques, and that too is an interesting open question. This is a regime in which, and we're talking about thick disks in which the sound speed is relatively high, and the precession time is slow. In fact, it might well be that the precession time is slow compared to the inflow time out to a significant radius. And that means that you just won't align, at least to the inner part of the disk, very well. There are also an interesting physics question about how an elliptical disk responds to lens-tearing torques. But, and the next promising graduate student has an interesting problem. Okay, I'll skip the next one. Okay, then, of course, most cases that we know about were found by optical and UV observations, and we now have a whole slew of interesting techniques for finding them. Let's see, can I list them from memory? What do we have? Pan-STARRS, GALEX, PTEF, Assassin, potentially Gaia, potentially EBOS, a few from Sloan. I'm sure there are more coming up in the future. And it'd be interesting to, I guess I'd like to hear more about the specific specialties they have in what kind of events they pick out, in which kind of galaxy, with what kind of luminosity and spectrum. That would be an interesting thing to look into a little more. And of course, there's also the problem of can we tell the real thing from imposters? And an important consideration in answering that question is whether we can define clearly what we're looking for. This was a question that Brad raised in yesterday's discussion, and I think is absolutely central to the empirical side of this business. How do we draw the boundaries between real tidal disruption events and other kinds of things? And are we missing interesting true tidal disruption events because of some limitation in our search methods? We're also beginning to move from looking at just continua to looking at lines, and that potentially can tell us a lot about perhaps elemental composition, likely atmospheric effects, the line widths and shapes, of course, tell us about the dynamics of the emitting gas. But to make good use of that, we need to know which gas that is and where. And that's not always so easy. Of course, an important question raised even before is, here we have all these TDE events in E+A galaxies. Why is that so? Are there any other varieties of galaxies that might be especially conducive to creating tidal disruptions? They're all equally open. Now, we'll move to X-ray observations. Oh, that's all cut off, isn't it? Oh, good. Okay. Now, what's that peculiar? Oh, I see. Yeah. So, you can probably figure out the missing letters here. They're typically only one missing letter. Anyways, so certainly one of the things we'd really like to know is the bolometric luminosity, especially given the theoretical prejudice that the peak in the spectrum is likely to be somewhere in the EUV or soft X-rays, which is a very hard region to observe. And it may be that those soft X-rays do provide the best measure of the bolometric luminosity. And now the question is, how can we get more measurements of it? Okay. But in fact, the scarcity of detections of soft X-rays from TDEs has raised the question of whether that's a case of that's missing in many objects, or whether for one technical reason or another we just can't see them. Another interesting possibility is a kind of indirect bolometer that Stephanie introduced is whether iron corona lines in the optical can serve as a kind of proxy for the X-ray luminosity. We also have questions about what kind of spectral or shape or time variation will qualify a flare in the X-rays as a tidal disruption and not just some hiccup in an AGN. Also interesting questions about the absorption lines. But in this context, I also want to cite a paper whose authors are, let's see, are there authors in the room? The lead author isn't. There's probably some of the other authors are. Pardon? Okay, yep, right, good. Okay, we've got several. Well, I'll tell you, the thing in your paper that caught my eye is this figure, which, oh, brother. That looks so much better on the screen and certainly so much better on the paper. So I'll have to tell you what these are. This is a linear scale, linear in flux and also linear in time. All these colored points are various optical and near UV points. These, which should be full error bars, are the X-ray flux. And what strikes me is that these are, number one, qualitatively different shapes. These are clearly following a power law. These are not. They're different. Okay. There's a little bend over here, but all this whole stretch, zeroth order, that's linear. Okay. So that's one thing, they're different. So the relation between the X-ray output and the optical UV output is not a simple direct one. Okay. The second thing that caught my attention is that this is the tail and this is the dog. The luminosity in the X-rays, in this case is of course 14 Li, is considerably greater than in the optical. The classic t to the minus 5/3 argument originally was supposed to refer to the bolometric light. So if we were following that argument, it's irrelevant whether the tail follows t to the minus 5/3. The important point is whether the dog does, and it doesn't. On the other hand, there are some of us who would argue that, in fact, the t to the minus 5/3 should be shown only by the tail, if it's due, for example, to those outer shocks, and that the larger part from material that actually gets closer to the black hole and has access to a deeper potential, if only the photons can get out, would follow a different time dependence. Absolutely. Except if you think this is a few 10 to the 6 solar mass black hole, this luminosity is 10 to the 44, so it's just barely grazing on Eddington. Okay, then we have radio observations. These are getting interesting, also particularly for Assassin 14 Li. And we had an interesting debate here about the nature of the outflow associated with that radio burst. So that's an exciting thing to follow up whenever two different reasonable groups can look at more or less similar data and reach quite contrary conclusions. Now, there's the issue of the jets. And after all, we've known for, what, since 1970? Most of this room wasn't alive in 1970. That roughly 10% of supermassive black holes that are accreting rapidly and are bright are radio loud and have jets, and the others have very puny jets. And so, in fact, when talking about tidal disruptions, which are the same kind of black holes accreting at more or less comparable rates, if you just ask a priori, what would you expect? You'd say, well, maybe it's like the AGN. 10% of them will have jets and 90% won't, or at least very weak ones. So that's kind of the zeroth order question. And of course, even with Sloan data, and it's hundreds of thousands of quasars, there are still arguments about the shape of that distribution function, the radio loud fraction. We have rather dicier statistics, so that's still an interesting open question. Okay, now, how about making the light? And this comes, or the Eddington limit question comes in, and it's interesting to my mind that we haven't yet actually seen anything that seems to be hitting the Eddington limit. Whether you think that super Eddington accretion is efficient or capped near Eddington, we haven't seen it. Because the former would say we'd see luminosities well above Eddington for the inferred black hole mass. There aren't really any examples except in the jet cases. And if it is capped, then you'd expect to see a plateau for a spell, and we haven't seen that either. So there's interesting physics questions about what exactly actually goes on. Then there's the question of, so we have this heat coming out, how does its spectrum get formed? And that's across the board, whether we're talking about soft X-rays or the optical. And this, by the way, is the one positive point that, confess at least personally, I came into this meeting not having realized this. I'm emerging from it, thinking this is definitely a true statement. And I think it's an important one because it really does color the way people interpret what they see. After all, we're talking about a rearranged star. Yes, it's spread over a larger volume than it had when it was alive, but it's not that much larger volume. And stars have incredibly huge optical depths. So whatever emerges is going to be through something that looks like a stellar atmosphere, which is not like a photoionized gas. And in particular, because the continuum transfer is much more complicated, the source function in the transfer equation is more important, both for scattering and for re-emission, and because the stellar atmospheres are significantly closer to local thermodynamic equilibrium than photoionized regions. And that's in the literal sense of how many transitions are near detailed balance in energy exchange. And the answer is many in stellar atmospheres and hardly any in photoionized gases. So that changes all the lore about line ratios and so on, and how the relative strength of different lines, that all needs to be thought of in stellar atmosphere language rather than AGN-style photoionization and I think this point was pretty clearly made in Nathan Roth's talk. Okay, now to event rates. So all the estimates made so far come in with rates of 10⁻⁴ per galaxy per year, or thereabouts. Something like an order of magnitude more than we see. And in principle, that could be we're predicting too many, or they're there and for one reason or another we can't see them. Either they're intrinsically dim or we're looking in the wrong way or something. And I was quote a conversation with Sturl Finney last night, who argued that maybe what's going on is that in these empirical measurements of the stellar density profile, that it's often hard to get into the region you really care about, and maybe those cuspy power laws roll over at smaller scales, and that would help suppress rates, but who knows? Maybe I'll already talked about that. Here, yeah, it'd be interesting if we could actually try to test the statistics. Once we think we know something about how the light comes out as a function of the stellar mass and black hole mass, then that should be something we can compare with those searches. And finally, we've thanked them. Oh gosh, the owner just went out again. I'd like to close with still more applause for the organizers, because I think this was truly an exceptionally interesting meeting and exceptionally well run. Both the for Sterling scientific committee, scientific organizers, and the superlative one-woman organizing staff. So just like to applaud them.